afternoon. I'm going to give a training session on hydrological and hydrologic models. So today I'm going to give training on the NashMod, which is conceptual hydrological or hydrologic runoff model, which is helpful for the estimation of runoff. We're saying that runoff model just is a string model, so it will help us to estimate the amount of runoff that will occur from the rainfall. Okay, so simulation model is a cascade of linear reservoirs. So by considering the consecutive reservoirs, okay, so we already seen on how the Nash model is functioning. So let's say we have consecutive reservoir, like reservoir Q1, so and reservoir Q2 and reservoir Q3. So in this, the principle of Nash as well now, Erla. So the principle of the overflow. Okay, so when the reservoir one fill, so the overflow that we call it in this Nash model, it's called recharge. Okay, recharge. So this recharge or the discharge will be discharged to the next reservoir, and then when the next reservoir fill again, it will be recharge the third reservoir. So this way the runoff process is okay. So having this concept of the Nash model, let us see how this NashMod, which is one of the model which is existing online. So we can download this NashM model, Nash model from the this website, okay, from the weather log. Just you can download it from this weather log. Okay, I can download it now here. Just copy this link. And go to Google, okay, so you can go to Google. Then click. So once you click, you will get these options. You can these options, so download options are on the right side. So you click on this NashMod. Then you'll get the URL zip file, okay, zip file. So I already downloaded it into my document here. Much more, okay, this is much more. I already downloaded it. So by downloading this zip file, then you have to go to your file and then extract the model from the zip file. Okay, just extract the model. Your folder. So just select this one. So this the model. So the model, once you extract the model, you can get it to the data set. So there are a data set is okay by default. Sorry. Data set. So this is a model. Then click on that model. For this, the model will attach on Indian will appear like this. Okay. So here there are file. So click in file. By default, the model will give you an input data. Okay, so from the extracted document, you will have material 1, 2, sorry, like that data. So for example, in material 1, these are inputs data. So you can open. Once you open, and so this is material input data which you will use. In this case, the data are extracted from the small valley in Robon. Okay, so the data is in millimeters. Time series data for 29, like 29 days. So this is for 1 month. Can say for 1 month. You extracted the data, and rainfall is in millimeter. Runoff is millimeter. So as we know, in it's mostly runoff or the stream flow data will give in terms of like a liter per second or a liter per second. So a liter per second. So there's or a meter cube per second. So conversion mechanism is needed. Conversion mechanism needed. So here to work on this, I try to develop here an examples. So from this example, here we can see that we take this power. Okay. So for example, if the rainfall data, if the time unit is, for example, now, as you know, the model by itself, this NashMod model by itself differs daily, okay, 1 day back. So the discharge, for example, the discharge given in our watershed is in like X meter cube per hour, while the catchment area is like Y meter square, then you should use this conversion factor, okay? So X is the discharge and then Y is the catchment area. So here, just we can do a conversion, like for example, when we are converting this, so this meter cube per hour should be converted to millimeter per day, right? So we have a catchment area. So here, meter cube per hour. You can multiply it to convert this out to the daily. So you have to multiply it with 1 day, 24 hours. We have 24 hours. And we are converting it to millimeter per day, right? 24 hours. And 24 hours per day, right? So 24 hours per day multiply it with divide it with the y meter square. So y meter square. So the meter here will be meter square, meter cube here. So these will omit meter square here, and we'll have a meter here. So this meter should be converted to millimeter. So as we know, 1 meter. And we're converting 1 meter to millimeter. Just it is 1000 millimeter, right? Millimeter. So multiply here. So 1000. So this will be here like this. Okay, 1000 millimeter. Millimeter per day. Multiplied by 24, right? We have 24 hours. So here how will be only divide hour. So we'll have per day, okay? Already we have per day. Then multiplied by the area, okay? So area is in meters cube. So this is how these units come up at the end here, okay? So you have to do the sum mechanism for all. For example, if you are going to convert in second example, if if the discharge is given in meter cube per second, mostly as we know, in hydrological stream flows, the data will be given by meter cube per second, even if daily. So you should convert while the catchment area, and mostly the catchment area will be given in kilometers square. Okay. So in this case, by using the same principle that we use in example 1, then the conversion factor will be like 24 hours, because here we're converting this meter cube per second, the data to given in meter cube per second to a millimeter per day. So the same principle we use. Second, in one day we have 24 times 60 times 60 minutes times 60 seconds. So this is 24 seconds per hour per day. So multiply it with x, which is a discharge given for us. Then we'll get the meter per, we'll get a discharge in this value. Okay, this value multiplied by x will give you m, right? M per day. Okay, so to convert this m to millimeter, you have to multiply it by 1000. Okay, so divide it with km2 or kilometers square, right? M the power of 2. When we're converting this to a meter, it's going to be 10 to the power of 6, right? 10 to the power of 6 meters square. So at the end, we'll come up with this factor. So this can be omitted here. So this will be like, sorry. So we should multiply the discharge given for us by 24 times 60 times 60 multiplied by the discharge divided by 1000. So at end we get millimeter. So the discharge will be millimeter per day. Okay. For example 3, for example, if the data given for you is in liter per second, and the catchment area given for you for us is in y meter square, so you will add in this conversion value. So by converting because in this NashMod, as which observed here, as observed here, NashMod, the data input data are yes. Let me take these pens. So the input data, rainfall and runoff, that is runoff is stream flow. Okay. Stream flow. Should be this should be in millimeter per day. You can see here. Okay, in millimeter, and rainfall should be also in millimeter, and this time series, daily time series. Okay, maybe daily, maybe in millimeter per second. Okay, it will depend on the your number of data. And the other point here is maximum storage and initial storage is maximum escape, but between the two like from one reservoir to the second reservoir. So as we know, runoff or the stream flow condition occurring through a river. So by the principle of Nash, as we know, so by just considering these areas a reservoir, okay, then there's the reservoir 2, then reservoir 3. So from this reservoir, recharge the discharge water should recharge the reservoir, and then it will come to once this fill the second reservoir fill, it will recharge the second reservoir, the third reservoir. Like this principle, okay. We already seen here last time. I already showed for years. here is a recharge. Okay, so this is a recharge from Q1, which is recharging reservoir 2, and again from this reservoir 2, it's recharging the reservoir 3. Once this reservoir filled again, charging the reservoir 3, and like this flow will occur in our river. Okay, if a discharge or a stream flow in our river. Okay. So this is the principle of NashMod. So this Nash, okay. So this NashMod using the principle of NashMod, and that this manner, and it come up with, it will give us an output discharge that will occur from the rainfall. So for the model calibration validation, we need rainfall and runoff that will occur from should be given as an input for the model. Having this concept, the other point in this model, the model calibration will be carried out by adjusting the maximum storage and the initial storage. Okay, so the maximum storage that will occur for in the first reservoir, and the initial storage may be the first reservoir have this, and then by just observing the coefficient determination or R square value. So this R square value should range from 0.7 to 1, which is the recommended value. So having this theoretical concept, let us train. Okay. So already, as already shown for you, once you open the model, so this you can see the information like information about. So I will show it for you here. It is how this model is functioning. So rainfall there. So rainfall once happen, it is charging our area. Then the escape time will be there. Then overflow. Then this overflow will recharge the second reservoir. And again, once the second reservoir fill, again it will recharge this reservoir like this. The model is functioning. Okay. So let us one more giving input for model here. This is the input should be prepared in time series. Okay, time series. So you can simply use the default, which is existing. For example, let's say this default existing clear one as an input. And then by preparing our data, for example, I want to apply this. In my case, I have this data, time series data. So let's say this is precipitation data of a year 2009 for my catchment, which is named Neri watershed, okay? And this is time series data. And this Neri watershed has a catchment area of 166 kilometers square. Okay, CQ. Yeah. So here we have a meter cube per second data, as I already showed earlier for use. We should convert this data to millimeter per day, right? So here the conversion you can do that already showed for you. We should give this one, right? We will give this one for the conversion. So let us do conversion here, right? So, all right. So I want to set my conversion here. So this is area, and then this chart that I have. So why here the X value discharge, and then Y value area in kilometer square. So here the discharge should be multiplied by 24 times 24 hours multiplied by second, minutes, and second. This is a number of total second that we have per day, multiplied by the discharge and divide it with the area multiplied by 1000. As I already told for use, we can omit here 1000, which will help that we use it for conversion of meter to millimeter. Is millimeter, because at end, as I showed for use earlier, we will come up with when we are dividing the discharge in meter per second with an area in meter square. So at end we will have a meter. Okay, so this meter should convert to millimeter. So here 10 to the power 6, we can omit 2 10 to the power 3 or 1000, omitting 0, 1000 above. So I just bring here this to my example. So this 1000 shows this value. This value, okay, this value, sorry. From this value, is the power 6. All right. So here, so once while you are setting this Excel formulation, okay, your linear equation here. So there's a linear equation that I'm going to set here to determine millimeter per day. So B2 shows the discharge, okay, day 1, minus 1 and 991, okay, this. And here you have to use a dollar function in order to make it common for all, okay. H2, okay, H column in the row 2, H2. So this should be set in dollar. So you have to use F4, okay. Use F4 to set it. First click on it. Sorry, first just click here and click here on your value, and then make it click on F4, so it will be user common for all. Okay. Then once you set, you just scroll down. You can scroll down, or you can just or easily just click here. Once the plus sign comes, click, then automatically do that's calculation for all your time series. All right. Now I have a rainfall data here, and my a plate that's going to go to located near, and this station is located in Nelly catchment or Nelly watershed. So then I wanted to do this for the means of, I want to do estimation of the runoff that will be generated to develop the unitary graph for the hydrograph for the month of October. Okay, October. So this mainly this one. Well, this means down to the runoff analysis by using the NashMod. So just copy this one. I'm going to copy this time series data for the month of October, right? And then just bring here just by using this transpose, okay? Just use transpose. Transpose October, November, December, October. No, sorry, just this one. Okay, then this one, October, end of October 20 years. So take this data, copy, copy this data, and then come to your data, and then just use the transpose function of pasting the data, and then so this is the time series data that I have. So I'm going to give for the memory model these real existing data. These are the default data. So here, in this case, the number of data is 29. So in our case, we have 31 data time series. All right, 31. So just set this value to 31. So it will say add data in last series at end of the column. Okay. So here we'll have 31 data. We'll just come here and then copy this your time series number. Then click on time series first row, paste, and you see like this time series number series will come, okay? And then again the same principle you have to use for the rainfall. Push up and then go to your data, time series rainfall data in millimeter that then copy, click, paste. All right. So it will come automatically. The same principle you use here for observed runoff data, or that's resting for data. All right, just bring this one copy, and then go to your model. Just click on the first row. Once these blue functions come, just copy paste. So this will be your item system. Now save your run. So I'm going to give the new name like Neri, okay? Neri. And say okay. Now the model run. So now the model run automatically while you are save and run. So the model will save on your data and input, okay? Then save. Then the model will save and run automatically. So to see our result, so here you can observe from this time series data from this maximum data storage, especially we are considering data storage to be now change the numbers for the runoff occurrence 15 millimeter, okay, and then initial data storage listen for considering the escape time 0.02 units number of reservoir just automatically to consider 5 maximum and alpha coefficient 0.0 which is automatically come from or calculated from our input data. As I said, recharge means the discharge to the next reservoir, okay? Generating. So graph, let us see the graph. So make a graph while you are on this pattern graphics. So there's option come at the bottom here, make graph. So just when you click on automatically take it into your data, so an area outputs that you already simulated. So we can do a hiding graph of runoff, and also we can also do the rainfall and discharge, or from the rainfall the discharge, the recharge that is indicating the discharge to the next reservoir, okay, and observe the calculated. Okay, we can see these these three outlines, and that the other point you should take care here is the R square that we call it. That is helpful for the model calibration. So in this case, this NashMod will be calibrated by adjusting the maximum storage and initial storage and observing the coefficient of determination to reach recommended value to optimal value. Okay, that will be a range of 0.7 to 1 optimal value. Okay, so let us do a calibration. Now here we have R square 0.73. Yeah, it's okay. So it's okay, but we can also do an adjustment. So here, by changing these values like maximum storage and shell storage, so let me decrease the initial storage by 27 rand. Again, you can, while you are saving, you have to save on the 7 area. Yes, and you have to observe. Okay, view the graph, runoff in time. There's no change. All right. So again, you can go to for mostly it's recommended to increase the maximum storage. Okay, by increasing the maximum storage, you can see the root mean or coefficient determination variation. So here, let's make this one 80 by maximum storage 8 millimeter. So here, let's see. All right, view graph, no variation over here. Import again. Let me increase to like 20. Save. So by doing this adjustment, if there is some variability, okay, we see there's some variability, like we now increase 0.74 while the maximum storage 80 and initial storage 20. Okay, let me make this one shows 30. I'm increasing. So this way you have to do an adjustment. Geograph, no variation, input, force, save. Okay. See, the pixel, coming to graph, no variation, 50. We're coming back to our default value. Okay, view. Yeah, it's decreasing. So here we should 40, 50%. So this is calibrated value. So without outputs, there's an output. So this is an output of our analysis. So alpha coefficient, rainfall that we give, and the Richard calculated runoff measured that we give runoff calculated. Okay, using the calculated value. That end the standard deviation coefficient 0.4 and then coefficient of explanation that we call determination R square is 0.4. So outputs will be this one. Okay, this is then our output. This is how NashMod is helping us. So you can see rainfall, recharge graph, so rainfall and rainfall that's okay, and then the recharge means, as I said earlier, the discharge. So rainfall occur actually, and then discharges occur around time this, okay, around 8. Around this 8 there. So this is rainfall down on the recharge. The blue shows the white shows the rainfall and then recharge. Okay. This is how Nash model is helpful for analysis of uh, the charge observed and calculated. Observed and this is calculated. So once we give a proper data for our model, we will get a proper graph of runoff graph. So this Nash model is very crucial, especially to see the runoff that will occur occurring from the input rainfall data. Okay. Rainfall runoff in time series is the runoff in time series. For the calculation of runoff in time series that we call hydrograph analysis. Okay. Yeah, things are clear. So this is a tabular output as we already observed from the training. Thank you so much. It's all about Nash model application for the development of runoff 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 versus time that we called hydrograph performance. Thank you.